Well, good evening. Welcome to this series of Heliophysics Big Year and Mathematics with Dr. Sten Odenwald, astronomer extraordinaire. He's part of the NASA HEAT team at Goddard Space Flight Center, the heliophysics team. So every month there's a webinar on a theme, and the theme this month is experiencing the sun. These webinars occur every month on the third Tuesday, so you can put it on your calendar. And we've planned an hour and then some time for you to ask questions. Everything is recorded and the slides are made available, so you can find those afterwards. I'd like to introduce Sten if you aren't aware of his work. He has a bachelor's degree in astronomy from Berkeley and master's and PhD degrees from Harvard. And he used infrared astronomy to investigate star-forming activity in the nuclear regions of the Milky Way galaxy. He's had numerous positions since graduating. In the Space Science Division of the Naval Research Laboratory, he was a postdoc and led a team of astronomers to support NASA's Cosmic Background Explorer mission. He was the lead of that group from 1991 to 1996. Then he was Director of Education and Public Outreach for NASA Image Mission from 1997 to 2002. Then Director of NASA Space Math since 2005. You can still find that online. NASA Space Math is an incredible resource of mathematics problems related to missions and the standards, the math standards. He now is part of the NASA Heliophysics Education Activation Team at Goddard, and he is an educator resource developer. In addition to numerous technical articles in astrophysics and education, he has published over a dozen books for the general public, including the 23rd Cycle, Learning How to Live with a Stormy Star, Patterns in the Void, Why Nothing is Important, Interstellar Travel, An Astronomical Perspective, Exploring the Heliosphere from the Sun's Core to the Interstellar Void. Dr. Odenwald has received numerous awards for his public education and writing activities, including the NASA Goddard Award of Excellence in Outreach and the AAAS Solar Physics Division Popular Science Writing Awards. You can find him on Amazon or your favorite bookseller, and they're wonderful gifts because a lot of the work is very accessible. I'll put this slide up again at the end. But this is the recording where you can find these webinars on YouTube. Okay, take it away, Sten.
All right, thank you, Hillary. Let's see if I can do this. Okay, share. And I've already gone past that. All right, let's put it in presentation mode. Slideshow, there we go. Okay, heliophysics big year. You're probably wondering what that's all about. Well, you're probably wondering what heliophysics is all about, since it's not a word you're going to find in your dictionary. Basically, it's the scientific study of everything about the sun, from the core of the sun all the way out to where the solar wind strikes the interstellar medium. That includes a number of phenomena that have to do with what we call space weather, which is sort of winds, flares, and storms from the sun that can affect our technology and actually hurt our astronauts if they are unprotected. The heliophysics big year is a 14-month, you could call it an extravaganza. Started with the annular eclipse last October, and it will end this next December when the Parker Solar Probe reaches its closest approach to the sun. In its studies of the solar wind and the upper atmosphere of the sun, called the corona. We've broken the year, these 14 episodes, up into specific topics that, these are not the things that you will find in a PhD thesis on heliophysics, but they're meant to encourage and entice the general public to take an interest in matters of the sun, in a variety of different guises, including citizen science. We already did an episode on fashion, which was really quite fun. And in the future, we're going to have things about the total solar eclipse in April, visual arts, performing arts, and so forth and so on. I encourage you to join our webinars each month as we explore these themes from a mathematical perspective, and you will be probably pleasantly amazed and amused at the particular tangents that we're going to go off on. NASA likes to organize its scientific thinking sort of after the fact in terms of three major questions in heliophysics. There are similar questions in planetary and astrophysics. Basically, what causes the sun to vary? How does the Earth and the heliosphere respond to these changes? And what are the impacts on humanity? That basically is the bottom line, and in large measure, why Congress has invested a lot of money in our pursuing this particularly obscure topic in science. It's not quite so obscure when you look at climate change and the effects that the heliosphere and heliophysics can have on the operation of our satellites in space, which are a non-trivial real estate totaling over $500 billion, in addition to quite a lot of people working up there as well. To break those three questions down into more digestible portions, which are suitable for teachers to interact with, our heliophysics group of educators, we've basically broken this down into a sort of a heliophysics tapestry or framework under which each of the three major questions has subsidiary questions, which are then more easily linked to the national science standards. Well, today, this month's theme is experiencing the sun. And of course, put your hat on as a geek and realize that the sun affects us through its gravity, visible light, solar flares, coronal mass ejections, and the solar wind. These are all the various ways that our lovely daytime star reaches out to touch us. Sometimes those touches are very pleasant, as though you're on a beach enjoying the sunshine, but other times it can be quite hazardous. And so it's a rather apropos topic to be exploring this month. Getting back to the educational connections, it's basically we're going to be discussing this theme as the sun is an active star and can impact technology on Earth. And it's made of a churning ball of plasma, causing the surface to be made of complex angular magnetic fields. So they're sort of the education standards that connect up with aspects of today's theme. Well, first of all, let's talk about gravity. Well, gravity is not really a force. Okay, you're all going to say, well, what is this guy talking about? Did he really get his PhD from Harvard? It turns out that we've spent the 20th century learning that there are three fundamental forces in the universe. The strong and weak nuclear forces, which are important for keeping nuclei together and causing other particles to decay. We also have the electromagnetic force, which is essentially anything that is touched by light or by electric fields or magnetic fields. All of these three can be described very neatly in terms of a theoretical physics theory called quantum field theory. And these forces are produced by the exchange of other particles, which we call bosons. So these three forces have a lot in common with each other. And you can basically use them in a weird interchangeable way if you're a mathematician. Well, gravity is not like that. Gravity is not a force in the same way that these other three things are. In fact, it's so different that physicists, Nobel laureates like Richard Feynman have said, well, maybe the fact that gravity is so different from these other three forces is a clue that we shouldn't really try to combine them, into the same definition. Well, anyway, I can go on and on about this because this is a subject very dear to my heart. But we're not really going to be talking about gravity this time, at least not at this level. Instead, we're going to talk about radiation, which is a nice, soft subject that we can all appreciate. Electromagnetic radiation is carried by particles called photons. They come with a range of wavelengths, and they carry, because of their differing wavelengths, differing amounts of energy. Gamma rays are the shortest wavelengths in the spectrum, and they are extremely energetic. You know, one punch from one of these things will blow up a nucleus of an atom. Visible light is sort of in the middle on a logarithmic scale, and radio waves are way at the extreme with the longest wavelengths. And everything else falls sort of in between this. Then we have the non-electromagnetic ways in which the sun touches us. I mentioned solar flares. We're now talking about the way that particles from the sun interact with the Earth and the rest of the solar system. Solar flares are created on the surface of the sun when you have tangled magnetic fields that try to rearrange themselves into simpler shapes, and they release an awful lot of energy within literally minutes. Some people have talked about, you know, literally thousands of hydrogen bombs going off at once, kind of a thing. As I said, the energy is stored in the magnetic fields. It gets explosively released. This can heat up portions of the surface of the sun to literally tens of millions of degrees. So for minutes to hours, you can actually get plasma on the surface of the sun that's hotter than the plasma in the core of the sun. But it doesn't last for very long because eventually the magnetic energy is released and everything returns to the balmy 6,000 degrees Fahrenheit that we all have learned how to know and love. But the thing is that these flares also produce blasts of X-ray light, electromagnetic light. It takes 8.5 minutes for this X-ray and visible light to reach the Earth. The X-rays have a really nasty habit in the upper atmosphere of sort of heating it up. That causes the upper atmosphere to expand out into space. If you happen to be a satellite in low Earth orbit minding your own business, all of a sudden you'll discover that you're on a trajectory which will take you into a decaying orbit and you'll basically burn up. This was discovered not long ago by SpaceX when they launched 60 of their satellites to low Earth orbit, and then they lost 40 of them because of this atmospheric drag effect due to a solar flare that had just happened literally the same day. Coronal mass ejections are a more dismal kind of a thing. You know, they're actually large clouds of magnetized plasma that are launched off into space by the sun. Again, the energy ultimately comes from these tangled magnetic fields that release the stored energy. CMEs, as they're called, travel at up to 3,000 kilometers a second, and they blast their way into the inner solar system and beyond. And when this stuff is directed towards the Earth, all of a sudden you find the Earth's magnetic field responding in a very dramatic way to this. You wind up with dramatic aurora in the north and south poles. You wind up with what are called magnetic storms, and then you can often get, for the very large storms, electrical power grid outages. You can wind up losing some satellites. Not really good stuff. And so scientists spend a lot of time trying to predict when these things are produced by the surface of the sun, or the corona more properly, and when the next one is likely to find its way in the Earth's vicinity. All of this is called space weather, solar flares, coronal mass ejections, high-speed wind streams, and so forth and so on. It's a collection of phenomena that are generated by the sun that are at different levels of risk to various systems on the Earth. Many of them are technological systems, but of course, if you happen to be an astronaut working in the space station or in the near future walking around on the surface of the moon, you need to know if there is likely to be a very powerful solar flare in the next hour or so you can take cover as best you can. The best way to take cover if you're a person working in space is to put as much junk between you and it as you can. So you tend to go into the interior of your spacecraft where you have a lot of bulkhead between you and the outside world. Many of the designs for lunar habitats and Martian habitats involve very thick walls made of the lunar or Martian regolith, which is a pretty good insulator against these high energy particles. So we learn a lot about space weather and how to mitigate it by essentially studying heliophysics. Yay, heliophysics. So this is a kind of a bad hair schematic of space weather on bad hair days, which basically occur almost all the time. You have solar wind coronal holes and cosmic rays. They produce a bunch of effects, mild geomagnetic storms, and satellites that sort of do wonky things in space that you're not expecting them to. So you basically have to correct whatever they're doing as quickly as you can. Then you have full-blown solar storms, which can either be the solar flares or the coronal mass ejections. And as you can see in this diagram, the energy from these events kind of percolates its way down into various phenomena and systems on the Earth. You usually get for solar flares about a 0 minutes warning, because as soon as you see a flare on the surface of the sun, it's already launched its X-rays into space, and 8.5 minutes later, guess what arrives on your doorstep? For coronal mass ejections, you can have up to like a 3-day warning. So that gives you time to actually do things to protect your assets. It sounds like a kind of a crude way of putting it, but assets is really what you're protecting under those conditions. So anyway, what does this all have to do with math? Oh, you're going to love this. I've partitioned this webinar into 3 sections: beginning, intermediate, and advanced. Here's the beginner section. We're going to do a little experiment which involves Venn diagrams and some interesting data about solar storms. So here's the setup for the problem. During a particular month, the following number of events were recorded. We had 22 big solar flares. We had 12 coronal mass ejections. And then we had situations where we had both a flare and a coronal mass ejection happening at the same time. So they're sort of related to each other. So based on this data, we're going to try to come up with a simple scheme for predicting when bad things are about to happen and what we can use as a clue to what's in store for us. So what we're going to do is, if you see a flare on the sun, what's the probability that a coronal mass ejection is also headed your way? And you can't really see it quite yet, but something is about to happen. So this is the Venn diagram setup. The blue area represents the 22 flares. And of course, we have 7 that are both flares and CMEs. So that's why I did 22 minus 7 to give you the 15. 15 is the flares that are not related at all to coronal mass ejections. They just simply seem to happen and nothing else happens as a result. Then on the coronal mass ejection side, we had 12 of those in total, and we had 7 that were flare related. So that gives us 5 in that white area that basically were not related to solar flares whatsoever. The intersection region in the diagram is the 7 events where we had both the flares and the coronal mass ejections. And so that's what we want to look at with this diagram. So here's what we're going to do. What we're going to do is calculate the probability that if you see a flare, that there's a coronal mass ejection on the way. So the way to do that is you look at the cases where you have both a CME and a flare, which is 7, and then you look at all of the flares that were observed, which is 22. So you get about a 32% probability, or a 1 in 3 odds, that if you see a solar flare, that a coronal mass ejection is likely to be coming your way. Now, the only qualification on this, however, is that we can see coronal mass ejections on the backside of the sun. All right, because as soon as they expand big enough, they become bigger than the disk of the sun, and they look, for all intents and purposes, like they're headed our way, like we're looking down the barrel of a gun. Ooh, I hate that analogy. So actually, instead of looking at 22, all the flares observed was 22, but there are going to be a whole bunch of other flares on the backside of the sun that might also be spawning some of these coronal mass ejections. Now, there are ways of accounting for this. If you assume that both hemispheres produce flares equally, then basically all flares observed is 22, but both CME and flare, if we have 7 on this hemisphere, we're likely to have 7 on the other. So that 7 is actually a 14, and that fraction should actually be 14 divided by 22. So that makes the odds not 1 in 3, but closer to 1 in 1 or 1 in 2. So, we can look at it that way. But we are observers on the Earth looking at the sun. We don't yet have satellites that are station keeping on the other side of the sun. So we don't really know if that number is 14 or closer to 7 anyway. But we do know that it's 7 because that's what we see here. So, this isn't a bad example. It's a good example for beginners to get used to, using Venn diagrams in this context. Now, for the intermediate problem, we're actually going to calculate the speed of an actual real flesh and blood, not a good analogy, coronal mass ejection. This is a coronal mass ejection sequence. It's the same sequence. It's the same coronal mass ejection seen over the span of about an hour or so on September 6, 2017. What we can do with the actual image is we can measure the distance from the center of the sun, which is that circle. Center of the sun is the center of that little black circle, out to some point on the edge of that coronal mass ejection image. And then we're going to use that same point on that edge in all 3 images and measure in millimeters what the distance from the center to that point is on whatever image we have. I happen to use this image here that's directly on my laptop screen. I just put my millimeter ruler up against the laptop screen, and I measured these numbers for the position 1, 2, and 3 of the CME. It was at 4 millimeters distance in that first image, 7 millimeters at the middle, and 12 millimeters at the third. So you've got the measurements. Now we also know that the diameter of the sun, which is that white circle, is 2 millimeters or 1.4 million kilometers. So very straight away, we can convert those millimeters off of the laptop screen into actual physical distances using 2 millimeters equals 1.4 million kilometers as our scale. When you do that, you get the positions 1, 2, and 3 in terms of millions of kilometers, which I call megakilometers. And we also have the times, which basically starting from that first image, we basically do the elapsed time. So the first image is 0, the second image is 30 minutes later, and the third image is 60 minutes later. And we get that from the times that we stated on the top line of the previous problem. Well, now we can calculate the speeds by taking the position 2 minus position 1 over 30 minutes, calculating that speed in kilometers per minute or in kilometers per second. We do that for the second pair, the middle and the last image, positions 3 minus position 2. And we get a slightly faster speed. In this case, it's 1,950 kilometers per second. So what this means is that when the coronal mass ejection is close into the sun, it's traveling slower than when it gets out to the edge of the corona, at which point it's traveling at close to 2,000 kilometers per second. So the physics that are going on within the inner corona are causing the coronal mass ejection plasma to accelerate as it's traveling through the corona into interplanetary space. What we can then do is, assuming that this coronal mass ejection in that third image had reached its terminal speed, which is speed number 2 of 117,000 kilometers per minute, we can work it out, because the Earth is 150 million kilometers from the sun, how long it's going to take that coronal mass ejection to reach the Earth, assuming that it reaches this constant speed in that last image and the speed doesn't change thereafter. Right? So this is a uniform motion, uniform speed, time equals distance divided by velocity kind of a problem. And as a result, we get 21.4 hours. So it's just slightly under a day. So at worst, if the coronal mass ejection is no longer being accelerated or decelerated, we could expect, having sighted that thing near the surface of the sun, that in about a day later, it's going to reach the Earth, if the Earth happens to be essentially along the direction that the thing happens to be moving. Now, for an advanced problem, we're going to take into account the fact that this is all happening within the gravitational field of the sun. And that means that as this thing travels away from the sun, it's going to be continuously pulled by the gravity of the sun, causing it to decelerate in speed. So it's not going to be moving at a uniform speed once it gets out beyond the corona. It's going to start slowing down as it travels farther and farther from the sun, constantly working its way against the gravity of the sun. So we're going to basically say, it starts out traveling at a particular speed, and we calculated 21.4 hours to reach the Earth. But let us suppose, and this is not a bad supposition, that the coronal mass ejection is slowing down by about 30 kilometers per second per hour. So every hour that goes by, instead of 1950 kilometers per second, it's going to be 1950 minus 30 for the first hour, minus another 30 for the second hour, and so forth and so on. So it's going to steadily slow down as it's moving out to Earth's orbit. Now, this turns out to be very similar to a ballistic problem. But let's take a moment and put all of these numbers into the same units, which are going to be useful for us. Instead of minus 30 kilometers per second per hour, which is kind of a dog's breakfast of units, we're going to turn that into kilometers per hour, because all of our interest is in how many hours is it going to take for this thing to get to us. And when you do that conversion of minus 30 kilometers per second times 3,600 seconds per hour, you get a lovely minus 108,000 kilometers per hour as the acceleration of this thing. And because, of course, it has a negative sign, that means it's actually a deceleration going on. And the initial speed, which is 1,950 kilometers per second, will convert that into kilometers per hour to get 7 million kilometers per hour. Now, the particular formula we're going to use is the standard ballistic formula, which is d is equal to the initial distance plus velocity times time plus 1/2 at squared. You will probably notice that we've got plus 1/2 at squared there instead of minus, because we're talking not about minus 1/2 g, which is things near the Earth's surface, but we're just in general talking about acceleration. And so this is the general formula. What we put in for A is going to take into account whether it's accelerating, which is plus, or decelerating, which will be a minus number. And so if we work this through and sort of reformat this a little bit, we know the sun, the distance 0 is 0. So that's the origin, it's the center of the sun. So d0 is 0. And then we fill in that we want the final distance to be 150 million kilometers. So capital D is 150 million kilometers. And if we rearrange the terms a little bit, we get something that's in the form of a quadratic equation. 0 equals 54,000 t squared minus 7 million t plus 150 million as the constant term. Now, this is a quadratic equation, and we can solve for t by using the quadratic formula. And we wind up with essentially two roots. And so now, as we do with all quadratic formula roots, we have to decide which of the two roots is physically reasonable and which one we can throw away because our problem isn't asking for that. So what we have to do is we're plug in the A, B, and C into the quadratic formula, turn the crank, and we find that b squared minus 4ac to square root term is 4.1 million kilometers per hour. And so now, true to form in the quadratic formula, it's minus b plus or minus that 4.1 million kilometers per hour. And so we get essentially two roots for t. We get a positive one if we add 4.1 million, and that's 103 hours. We also get a negative one, which is 26.9 hours. And the 103 hours corresponds to the coronal mass ejection traveling out into the solar system, slowing down to zero, and then falling back into the sun. Well, we don't care about that because we're pretty sure that we don't have enough details in our formula to make that a physically reasonable scenario for that second route. In fact, what happens is as the coronal mass ejection slows down further and further, it starts merging into the solar wind, which is constantly traveling at about 250 kilometers per second out towards Pluto and beyond. So the CME, once it gets down to these very slow speeds, is then going to interact with the solar wind, and we haven't factored that into this ballistic equation at all. But we can use that first route, the minus route, to get 26.9 hours, and that corresponds to the thing actually arriving at Earth's orbit at 150 million kilometers. Now, the 103 hours is also relevant to 150 million kilometers, but the direction is that it's returning through that, going back towards the sun at that same distance. So it's a different scenario entirely. Now, after 26.9 hours, we can actually calculate what the speed of the coronal mass ejection is going to be after all this deceleration has happened. And we know that the velocity is equal to the initial velocity, which is 1950 kilometers per second, plus the acceleration times the time. And the acceleration, as we noted, was minus 30 kilometers per second per hour. Multiply that by 26.9 hours, add that to the 1950, and you find out that the speed of the coronal mass ejection at 150 million kilometers is about 1,143 kilometers per second. Well, that's a lot different than 1950, which is where it started. So we've seen that the effect of deceleration is a significant effect. And it has a significant impact on how you calculate the arrival times. Instead of 21.4 hours, which is what it was doing if it were just coasting, it's going to be a little bit longer. It's going to be 26.9 hours. You know, that's a 5-hour difference. That's almost a full workday. There's a lot you can do in a workday if you're trying to mitigate effects from an incoming coronal mass ejection. So that's why we have these very powerful computer programs hard at work crunching data using much more sophisticated equations than I've shown here to actually calculate this number as accurately as we can. So anyway, between the beginning, intermediate, advanced aspects of this problem, we've pretty much covered how the particles affect the Earth and how they get out here. And I hope that you'll be with us for the next episode, which is going to be the total solar eclipse, which we're all waiting for with bated breath. Okay, that's it for tonight. See you next month.